Okay, good afternoon. So today, hopefully, I have some slides left from the concepts, and hopefully we run through them really quick, and we can start talking about multi-threaded kernels. Okay, so in the last lecture, the last thing that we talked about was user to kernel and kernel to user mode transfers. This one is kind of like showing you that in one picture. So usually the things to note here is that the user has limited hardware access. Basically, not all the instructions, not all the regions of the memory are available to hardware to the user program, whereas kernel has full access to memory. So whatever code that we run in kernel mode can do whatever it wants. So usually we start at kernel mode, right? And then we start executing user mode. At some point, the user mode may exit. We again come back to kernel mode, or maybe your user code calls the system call. We transfer back to the kernel mode. We go from kernel mode to user mode by return instruction that returns from exceptions, RTN. Interrupts could happen. At the time of interrupt, you might want to go and modify the hardware and come back, go back, return, and it eventually return from interrupt RFI back to the user. Exceptions could happen, and so on and so forth. So that's kind of like where we are now. We talked about system calls and system call handler. Let's dive a little bit into that topic. System calls are basically the interface that user programs get to access devices. And when the operating system handles a system call, at some point it might need to talk to hardware. Now, there are plenty of different types of hardware, and it really doesn't make sense for us to implement them all in any distribution of operating system or Linux you produce. So usually the manufacturers of the device write the device driver. And that's the code that unfortunately has to run in kernel mode to talk to the hardware. And I say unfortunately because in some cases, for instance, in NVIDIA drivers, we don't even know what that code is doing. But nevertheless, in many cases, we give that code full access. So we run device drivers in kernel mode. And unfortunately, again, we don't have any options. Now, you could, go look at the hardware specification and write an open source driver. For example, many USBs, they just use a common library to write the drivers for USB devices. Some of NVIDIA GPUs have open source drivers, but usually you don't get the highest performance because there are tweaks and details that might be too time consuming to get to the bottom of. So usually the drivers that we get from manufacturers are the ones that work the best, and usually they're proprietary and we don't get to see their code. And nevertheless, we sometimes are forced to run them in kernel mode. Now, with that, usually the terminology in Unix systems is that we divide device drivers into two halves: the top half and the bottom half. The top half is accessed in the call from the system call. So when you when the user calls the system call, usually the top half of the device driver gets activated and runs, and this half sets up whatever needs to be done, right? If you want to open a file, if you want to read from a file, or you want to write to a file, initially the device driver wakes up or gets called, more precisely, and it sets up the device to do what it's supposed to do, to read from memory or write to the memory, or do certain computations, whatever that be. Then once this is done, we kind of are done with the top half. Now, after the top half is done, the device starts working on the instructions that it has received. And at some point, the device is done with what it's supposed to do. And at that point, the device raises an interrupt, usually. And when the interrupt, so the top half got to execute after the system call. Now the bottom half gets to execute after the interrupt is raised, indicating that the device is done with what it's supposed to do. And at this point, the bottom half runs in the interrupt handler. So you detect whatever interrupt that has happened, and then you handle that. That we usually call the bottom half of the device driver. So let's look at it in action. So the first step here, let's start with the user request. This in the form of a system call. So let's say you want I/O. So you use system calls to tell the operating system that you need what you need. Then inside the operating system, before we even go to invoke the device driver functionality, we check if we already can, do what you want. For instance, if you're asking for a file, to read a file, and we already have the content of that file from SSD in our memory, the kernel could just return or copy that data for you and return to you without even invoking the device driver. So you might end up, if the data is ready, you just go back to the user program. However, if it is not, if operating system cannot by itself handle your request, then the top half of the device driver gets activated. So we send a request to the device driver. The device driver starts setting up the hardware and telling the hardware that you need to interrupt us once it's done. At this point, the hardware starts working. So whatever needs to be done, let's say you wanted to write to the file or read from a file. Now your SSD is bringing the data or copying the data from SSD to memory. Once it's done, the device will raise an interrupt. When the interrupt is raised, the bottom half of the device driver wakes up or is invoked to handle that, right? Now the data is ready. What should I do? Now the device driver does what it needs to do, and passes the data back to the top half, and then that is passed to the kernel, and then eventually kernel copies that data to the user process, to the user process's virtual address, and we're done. So this is kind of like in action, talking about top and bottom halves of the device driver. Now, we talked about, I kept saying the device transfers data, either from memory to the device or from the device to the memory. Now, this is usually done in two ways. Either we do programmed I/O or we do direct memory access. What is programmed I/O? Programmed I/O is to basically get the CPU involved in each byte of the data that needs to be transferred to the device or from the device. So you basically execute instructions in your CPU for each byte of the data to be transferred. Now, this is kind of simple and easy to program. If you want to, let's say, read 1 gigabyte, so you go through all the bytes, and then for each one of them, you will execute an instruction to transfer the data. But it's kind of like wasteful because you're using CPU cycles to do this transfer. The alternative is to do direct memory access. In direct memory access, you kind of set up the device, and the device, or in particular the DMA engine, starts moving byte by byte, and then CPU can do whatever it wants to do, right? So direct memory access is possible if you have extra hardware in the form of a DMA engine that can that the CPU can delegate the job of transferring bytes to, so that the CPU can spend its cycles on running the programs instead of transferring the data. Now, there are steps if you want to do DMA. So the first thing that has to happen is to run the device driver. So the driver starts running, and what it does, it tells the DMA engine. Now, when I'm talking about DMA engines, I have to note, in older systems, there was 1 or 2 DMA engines that were shared by all devices, right? So it would come inside your processor chip. There was a DMA engine that would then, communicate with the devices. Now, in today's day and age, most of the PCIe devices that you buy, they have inside themselves bunch of DMA engines. So each device has 1 or 2 usually. Some of them they don't. And for those, you go with the old-fashioned using the DMA engine available on your board. But for most of the devices, like let's say your GPU has its own DMA engine, your SSD has its own DMA engine, your NIC card has its own DMA engine. So then the device driver runs on the CPU, talks to the DMA engine inside the device, gives it instructions, tells it how much data should be read or written to memory from the device or to the device. So this is what happens. So you instruct your device, and in particular the DMA engine inside your device, and then your DMA engine starts transferring bytes one at a time to the memory, right? So now you are transferring data. Okay, so in this slide, I have to clarify. This is the old system where there is a DMA controller. So that's why we have this step 3 and step 4, where the device talks to the DMA engine. But in modern systems, as I said, this DMA controller lives inside your device. So each device has its own DMA controller, right? This picture is for the old systems where there was a single 1 or 2 DMA engines that all devices could share. But anyhow, so you got the idea. Now the bytes of data are being transferred, and in the meantime, CPU can do whatever, it can execute whatever they want, right? So the CPU could now be executing some other process, while the DMA engine is transferring bytes for another process, right? And once it's done, the DMA engine raises an interrupt. So we tell the CPU that we're done. The data has been transferred, and now you can do whatever you wanted to do. So this way, we kind of save CPU cycles, right? So I got a question, device driver equals DMA? No, the device driver is a code that you run to communicate with the device. Now, your device driver can set up the DMA transfers. So that's what we just said. Okay, so here's an example, another example. Let's say this is a DMA example for networks communication in Linux kernel, right? So in this picture here, I have the physical link. This is the physical link that is connected to your NIC. Now this is your NIC. This is the physical memory region that is associated to DMA transfers. Now this one is the region of memory that is associated to kernel, and this is the user's memory, right? So we start from here. Let's say you get a packet on your physical link. Now this packet is written to the device. So device has its own, hardware. So it's there now. And when your device gets the data, it writes them to the DMA. It DMAs them to the physical memory. Once the copy is done, we go back to the device, and device raises an interrupt. So this is the IRQ. The interrupt has happened. Now, this ring has to be set up by the operating system, right? The operating system should tell the NIC that if you got packets, you have to DMA them somewhere, right? And to set this up, the device driver does that, right? Otherwise, how does the hardware know where to DMA the data, right? So before all of this, we need to run the device driver, and the device driver comes and configures your NIC and tells your NIC that if you got a packet, DMA the data for that flow to this address in physical memory, this DMAable memory region. Okay, so now where were we? So interrupt happens. Now the kernel, the bottom half, right? If you remember, after the interrupt, the bottom half starts running. And what it does is it copies the data from the DMAable region to the memory buffers in kernel space. Once that is done, and at some point, right, you want to give this to the application. So you start copying it to your application. Okay. Yeah, so when your application says socket receive, wants to receive, then you copy them to your application's memory. Now, you might at this point think, okay, like, when was the last time I saw system calls? I've never, called trap in my code, right? There was no trap instruction that I ever used. So where are these system calls? And you're kind of right. You probably have never used system calls directly. There has been always, though, a level of indirection. So you always go through your system libraries like libc, and those guys usually do this for you. So you call on them, and they internally call the system calls in your system. So this is basically how this figure comes into play, that you have all these applications. They're going to use these portable OS libraries, and these OS libraries are going to communicate with the operating system through this system call interface. And this system call interface is going to talk to devices through device drivers. And the device drivers are going to then go and talk to the devices. Here's an example. This is the last example from this lecture. So just to put everything together, let's assume that we're looking at a web server. Now, clients are sending requests, and the web server is basically a process that is running on a server to do some service, right? Maybe it's a file web server where people send you requests for certain files. You go look them up in the server, you find those files, and then you transfer the data for those files to your clients. Or maybe it's a, instead of a web server, it could be an email server, or you name it. Now, let's focus on this web server process and see how it works. So this is like, I'm looking at that hardware, that physical server. So there is an operating system running. The hardware is here, and this is my web server process running on top of the operating system. Okay, so initially, your web server opens a socket, probably, and wants to read from that socket. So it calls through system libraries a system call, and it goes to the kernel, and it starts waiting, right? At this point, your I don't understand this question. Somebody is asking, why is the reply retrieved by the web server? Can you explain your question? Okay, so now, after this system call, let's say it was a blocking system call, you wanted to read a socket, so the process gets blocked. There is nothing more for you to do at this point. You're going to just wait. Then let's say requests come. They go as we saw in that picture, the DMA stuff, right? The data eventually gets copied into the memory of the kernel, so it's in some buffer right now, right? Now, so again, interrupt happens, and then the data has been copied by the DMA, and then an interrupt happens. Now, the operating system at this point has the data that you wanted, so it returns from interrupt. It copies the data for you to the web server's memory, and then returns to the memory of the returns to the web server process. Now you have the data, you process it, you see that, oh, this is a file. You then call another system call to read the file that you want to send back to your users. So again, this happens. So the disk request is issued to read the file that you want to read. Once the data is DMA'd to your memory, you have it in your buffer, and then eventually, once you have the data, you go back to the process. You say, I have the data you wanted, and finally the data is sent through another system call to send the packet to the users. So this is kind of like you're looking at how many system calls and interrupts and so on and so forth. Give me a second. Sorry. Okay, so I got a question here. Why is the reply retrieved by the web server on the previous slide? Yeah, so basically, for instance, this is basically in the context of, let's say you wanted a file, right? So you send a request, and the web server retrieved the reply, the result, the request that you wanted, and then sent it to you. That's what it means. Does RTU stand for return to user? It's a return from exception. RTU. I don't exactly know what it stands for. Yeah, I don't exactly know what it stands for. So you have return from interrupt and then RTU, but both of them do the same thing, right? They go from kernel mode to user mode. Okay. Oh, this last step I forgot. So then you basically DMA. Once you have the file that you want to send, you DMA it to the NIC, and then NIC sends it to the client that asked for the file. Okay, so in summary, in this lecture, I mean not this lecture, but in the past few lectures, we looked at 4 OS concepts: the thread, address space, process, and dual mode operation. And in the next lecture, in the next series of lectures, in fact, we're going to look at implementing now threads and processes in an operating system. Okay, so let's go and look at the next lecture. So we're now looking at multi-threaded kernels. I'm almost on track. I think I'm 30 minutes or so behind my schedule, but okay. Okay, somebody is asking, so is return for interrupt for returning to user mode for interrupts and RTU specifically for system calls? So the reason I'm not actually, you shouldn't worry about this RTU or RTI is because different architectures have different instructions. I believe RTU is something in x86 and RTI or RFI. So these are instructions to switch mode. And different architectures have different instructions. So the concept is important. The specific instruction is not important because, you know, RISC-V has its own instructions, ARM has its own instructions, x85 has its own instructions. So we shouldn't worry about what instruction is for what. We shouldn't be worried about what we need to do and what is provided by the hardware. So the bottom line is when you're in kernel mode, because of interrupt, because of system calls, because of exceptions, at some point you want to return to the user, and there are instructions for you to execute to return, right? And if I'm not mistaken, there is an instruction for you to go from interrupt. So if you went to kernel mode because of interrupts and you now want to come back from your interrupt handler, you do RFI, I think, I'm not sure. And if it was like a system call handler and you want to go back to the user mode, you call RTU or something. So anyhow, so there is an instruction for you to return back to the user, given that you want to transfer mode and whatever that entails that we discussed. Okay, so the third topic that we're going to cover is multi-threaded kernels. What are we going to see? So the first part of this series of lectures, we're going to talk about how we can implement threads. So in ECE 252, you've been introduced to the concept of threads and processes. And so far in ECE 350, we just reviewed them again. And added some more information about dual mode operation. Now, in these lectures, we're going to see how we can implement threads. And the second portion of the third part of the lectures is the two types of threads that might exist in a system: kernel versus user-managed threads. So we talk about that. And the last part, we'll talk about how we can implement synchronization objects inside kernel. Again, in 252, you learned about mutexes, you learned about semaphores, you learned about condition variables, and you used them to code. So that's good. So you know how to use them. Now, in ECE 350, you're going to learn how to implement them. You probably saw some discussions about implementations, like test and set, for example. But we're going to dive deep into implementing these objects. OK, so this is a whole picture that we're going to focus on in our implementation. So what are we seeing here? So we want to implement this guy, this kernel guy. Now, our kernel is going to have a bunch of kernel threads. And by the way, these lectures are kind of put together around your labs, right? So it has some specific parts that are related to the labs that we have. So they might not be that general purpose, but I still try to give you the whole idea, regardless of the RTX that we're implementing in our labs. We also want to know about kernels, right? So, but anyhow, most of the kernels that you're going to have, including the RTX that you're going to write, supports kernel threads. So these are threads that run in kernel mode. Now, we also want to run threads in user mode. So we're going to have user processes. Now, in your RTX, we're not going to have processes or threads. We're going to have tasks. So we're going to have a bunch of kernel tasks and a bunch of user tasks. But in general purpose operating systems, you're going to have a bunch of user processes, and each one of them could have a bunch of threads. Now, as we discussed, the operating system is going to allocate separate stacks per thread. Operating system is going to create TCBs per thread. These TCBs, operating system has TCBs for its own threads as well. And operating system has PCBs for the processes inside the user processes that it has created. Now, in this, in the process of creating a new thread or creating a new process, the first line is the system library. If you remember in the previous lecture, I mean, in a few slides ago in the concepts, we talked about system library being the one who receives the request and then calls into the system call. So when you want to create, let's say, a new thread in C, libc starts by creating your user stack for you. And then at some point, your system library calls it a system call into kernel so that the kernel can set up everything that it needs to set up for your thread. So the kernel then sets up kernel stack, the kernel sets up your TCB, and whatever else that is needed for this thread to be created. And once this is done, the kernel puts the TCB, the newly created TCB, on the ready list. So we talked about this ready queue, right, if you remember. So the ready queue has all the threads that we want to execute at some point. Now that this thread has been created, I'm going to put it on the ready queue so that whenever the time comes, this thread is going to be executed. OK, just to recall, we talked about different states for thread, the initialization, which the kernel has started creating the thread. Once the thread is completely created, then, as I mentioned, the kernel puts it on the ready list. So the state of the thread becomes ready. If the thread is scheduled, then its state becomes running. If it's waiting, its state is waiting. And once it's done, the state becomes finished. Now, let's focus on going from ready to running, and also going from running to waiting. So what triggers a context switch? So first of all, what is a context switch? Context switch means switching from one thread to another thread. So if the unit of execution in your system is threads, so it means that we're going to go from one thread to another thread. So that's context switch. So we were running thread A, now we want to run thread B. Now thread B could be from the same process that thread A was, or thread B could be from a different process. We don't care. So we call both of them context switching. So we're context switching from thread A to thread B. They both might belong to the same process, or they might be from different processes. So that's context switch. Now, what triggers this context switch? Why would we go from one to another one? So there are two types of events that could happen that would trigger a context switch. The first one is a synchronous event, which basically means that one of the threads, the current running thread, called a system call. That system call could be yielding or joining or writing or reading, right? When you call a system call, you might get blocked, right? Let's say you want to read a file and the file has to come from SSD to memory, and that takes time. So you're going to go and get blocked, or you're going to go to waiting. So because of that, the operating system now wants to context switch from you to another one, because it's wasteful to stay with you when you cannot do anything. You're going to wait. So this is a synchronous event that leads to a context switch. The second, so this is an example. For example, let's say you want to calculate pi, and you don't want to get the CPU all for yourself, right? So you write this while loop. I'm not saying that you should write it this way. This is just an example, right? So you calculate one digit, and then you call thread yield. In case, let's say, there is some other thread in your system that wants to run. I got a question. So in our labs, process equals threads equals tasks. In your labs, thread equals tasks, and we don't have process, or we have only one process, that one user process that owns all the user tasks, and then one kernel process that owns all the kernel tasks, right? But if you feel better, yeah, maybe process equals threads equals tasks in your project. But more, if I were to just say it more carefully, in your project, there is we have user level tasks, but then because we don't have any memory protection, they have access to the entire physical memory. So that's why I'm saying there is no process, because we're not, when you talk about process, you really want to talk about isolation. We don't have any isolation in RTX that we're designing, right? So all the tasks can access each other's memory, including user tasks can indeed touch kernel tasks memory, right? The reason we don't have it is because it would be painful to ask you guys to implement it, right? So implementing this memory isolation is hard, so we just forego that. Therefore, we don't have this process notion, right? That's why I'm saying tasks are like threads, because they can all touch everything that is available in physical memory. Okay. So we talked about the first type of events that could happen, synchronous events. The second type of events that could trigger a context switch is asynchronous events. And these are basically interrupts and exceptions. In fact, I made a mistake. So here it should be interrupts and exceptions should move up here because exceptions are synchronous events. So because you cause exception, you divide by 0 or you access a memory that you were not supposed to access. So I will fix this slide. So synchronous events include system calls and exceptions, and asynchronous events basically has the interrupts in it. So an interrupt happens in the middle of wherever you are, and that is considered asynchronous event. And because of an interrupt, you could potentially, OS could context switch. It's not necessary, but it could trigger a context switch. For example, a timer could go off, an interrupt is raised, and operating system decides to context switch. Or maybe operating system doesn't want to context switch, right? It could trigger a context switch. Maybe let's say you are running your process and a packet came, operating system decides not to context switch you, even though it raises an interrupt. Operating system deals with the interrupt and comes back to you. It doesn't context switch, right? But it could also trigger context switch. Now, how do you handle a context switch? This is a typical, I actually want to go to PDF version because PDF looks much better. The code that I wrote, the font is much better. So let me open the PDF so that we can use the PDF. Okay. Okay, we're here. So this is a typical handler. And as we saw previously, there might be different types of handlers, right? You might have interrupt handler for timer. You might have divide by 0 handler. You might have system call handler. But if you look at them, they usually have this skeleton. And what it does is usually at the beginning of your interrupt handler, you push the registers that might change during the handling of this interrupt, right? So don't forget, we were in user mode, we were running user code, something happened, we switched mode, and now we're running kernel code, but we don't want to lose the user state, right? Because we eventually want to go back to that user program, probably. So we need to save the state of that program. Now, if we are going to use some of the registers for kernel code, then we need to save those registers because they contain the data for the user process that we were running. So if you look at most of handlers that you can look at the beginning of it, they save the state of the processor. So I think we discussed this in the previous lecture. You could just have a convention that says I restrict all my handlers to only use, let's say, R0 to R5. And they're not supposed to touch anything after R5. And if you make that convention and stick to it, then you don't need to save R6 until the end because your code is not going to touch them. And you can just save R0 to R5. But in RTX that you're working with, if you look at the handlers, if you look at the system call handler or the IRQ handler, you see that we are actually saving all the registers. So it's easier because you don't want to have any convention that restricts you which registers you're going to use. But it's a little bit, the overhead is higher because you have to write more to memory, and going to memory is basically expensive. So after you take that step, then the code comes to handle your interrupt, to handle that event. If it is an interrupt, if it is a system call, whatever that is, you handle it. And finally, once you're done, you want to return. So when you want to return from the handler, you pop those registers that you pushed, and then you return to the program. And this return, right, changes your mode if you're going to go back to the user code, right? This is not a, returning from a function. This is returning to user mode. Now, please pay attention to this guy because I'm going to use it later. So I have annotated this line because we're going to use this last piece of interrupt handler in future. When it comes the time, I'll mention. But anyhow, so this is like a typical handler. I got a question. When you mention interrupt, you only refer to interrupts that do not involve memory operations. In some OS, memory is accessed through interrupt. Memory is accessed through interrupt? I don't. Interrupt, for example, then I sort of don't understand the question, so if you can clarify, but I still will try to answer it somehow. I'm not just, so interrupt is an event, right? It indicates that something has happened. What is that something? That something could be a packet has arrived. That something could be a DMA has finished. That something could be timer has expired. Another one could be, what else comes to my mind in terms of interrupts? A key has been pressed on your keyboard. When you press a key, that causes an interrupt. So it's in the terminal, some character was input. So these are interrupts. Now, interrupts could involve, processing interrupts could involve memory, right? For instance, if a packet has arrived, now I want to read it. Where is it? If a DMA has finished, the data is probably somewhere in my memory, or I know that now the memory that I gave, the file that I wanted to write to SSD has been written to SSD, right? So hopefully that clarifies the relationship between memory and interrupts. So interrupt is just an event, but it usually concerns some data, right? A key has been pressed, a packet has arrived, your DMA request has finished, so on and so forth. Okay. Now, let's go. Okay, I have to use my PDF on my slides, unfortunately. Yeah, the font I used is not defined in my tablets. That's kind of, that sucks. Okay, so we are talking about context switching. Now let's look at the code that does the context switching. I'm going to call this code thread switch. So remember it. We're talking about thread switch. What are the inputs? So the first input is old TCB, and the new input, the next input is new TCB. So I have two TCBs as expected. We want to context switch. We want to go from the old thread to the new thread, right? I have two threads. I want to context switch between them. Now this thread switch is kind of like a special function. When you go there, your SP, a stack pointer, is pointing to the stack pointer of old TCB. And when you get out, the stack pointer points to the new TCB's stack. So because what is a function really? Function is a piece of code. What is the context of a function? It's the stack, right? So whatever is on the stack kind of dictates the context of the function. Now, if I'm coming to this function with one stack, and get out of this function with another stack, it's as if I came to this function in the context of old TCB, and I'm getting out of it in the context of new TCB. And that's all because I changed the stack pointer. Now let's look at all the steps in this function. The first step is to push all the registers on the kernel stack of old TCB. So let's copy the state of this old TCB. Now that I want to context switch, I'm going to copy everything, right? So in x86, this would be push AD, right? In ARM, you have to specify what registers you want to push. If you look at the thread switch code in your starter code, you will see that we're pushing all the registers in thread switch. Next step is to save the stack pointer on the stack, right? So now a stack pointer, it's a register, right? A stack pointer is a register. It's pointing to the old TCB's stack, to the top of that, right? I'm going to save this in my TCB. So TCB is the thread control block. It potentially has a field called SP. So this is a data structure that the kernel is keeping for each thread. Now that we want to context switch, the kernel wants to remember where the kernel stack of this guy was. So it saves the SP, this register, into memory, right? So we save it in our TCB. Then next step is where we switch stacks. So then we set the stack pointer to new TCB's SP. So new TCB SP has the stack pointer of this new thread that we want to context switch to, and we set the SP to point to that address. Now that we're looking at the new stack, we pop all the registers. This is where we context switch, right? Now I have a new stack for the new TCB. Now there are a bunch of registers there. I'm going to pop them. And when I pop all the registers, now I am where I was last time I context switched on this thread. And once that happens, I can return. So this return then returns to wherever this thread switch was called in the old TCB. So to just tell you, like, I have slides for this, but here, let's say I have thread A and I have thread B. So initially, let's say I want to go from A to B, and this is the stack of A, kernel stack of A, and this is kernel stack of B. Now, when I come inside, let's say initially A is my old and B is my new. So I push the state of thread A, CPU state here, and I switch to B. I go to B, and later on, I want to go from B to A. Then B becomes old, and A becomes new. So next time I want to go back to A. So when I come, this time I push the CPU state of B on the kernel, and then I swap the SP to point to the kernel stack of A, and now I'm here. So then I pop everything that I pushed last time. So now I have the context of A, and I can return. Okay, so let me delete everything here. Okay, so now what is this new TCB? As I said, now this new TCB is either, like the example I just told you, is either a thread that we previously context switched from, and now we want to context switch back to. So at some point we context switch from A to B, and now we want to go back to A. So that's one scenario. The second scenario is this new TCB is a newly created thread. So maybe we never have executed this thread. This is the first time we want to execute it. So these are two cases, and we have to be careful about these two because they're slightly different, right? One of them, we previously popped stuff on the stack, and one of them is a new thread. We never have been here in thread switch for this newly created thread. This is the first time we're running thread switch on this thread. So one of them previously we have done this push for, but the other one is a newly created. It has never been an old TCB in any call. So we have to be careful about that. Where should we be careful? It's here. When we are popping, what are we popping? Here, right? So it depends. If this TCB is not a newly created thread, if this TCB is for a thread that was running before and we context switched from, and now we're context switching back to, then we're going to just pop everything that we pushed last time. So we're going to pop everything that we pushed here in this line. If, however, this is a new TCB, we're still popping, right? We have to be careful. When we create this TCB, we will have to put some dummy data frame on the kernel stack of this TCB so that when it comes here to pop something, we need something to be on the stack. If we don't have anything on the stack, we're going to still pop, and that could mess up our stack pointer. So in order for us to have something, doesn't matter, we can just initial all the registers to 0. So we can just, when we create the thread, we push this dummy data frame, all zeros, so that when we pop it here, it makes all the registers to 0, for example. The second point to be made here is, where does this return go when we return? If you remember, when I was talking about a stack, I told you that return always goes to the return address on the stack. Now, what is the stack that we're using, right? We're using Kernel Stack because this is kernel code. Now, we entered thread switch with the stack of old TCB, and we're getting out of it with the stack of new TCB. So when we get to this return, we're going to look at a stack of new TCB and see what return address is saved there. And we just go there, right? Now, this also depends on this new TCB being a newly created thread or an old thread. If it is an old thread, then it's gonna be easy, because at some point on that old thread, we called thread switch. So some function called thread switch. So the return address of that function, or the next line in that function, is already pushed on the kernel stack. So we're okay. If it is an old, it's not a newly created thread, we're gonna just go to wherever new, thread switch was called. If, however, this is a newly created thread and it's never, thread switch has been called on it, then again, during creation of this thread, we need to push the return address. Now, where should we return really if it is a newly created thread? We probably want to return to the entry point of this thread. We want to go and start running this thread. Now that this is a newly created thread and we're context switching to it, so where should we go really? We should go to somewhere that we can start running it, right? That's the entry point of the thread. Okay, so two things now we're gonna, I'm assuming that you kind of learned here. that we need to take care of these two when we are creating a thread. We need to push some dummy data frame. We also need to push the address that we want to return for the first time. Sorry, we want to jump to for the first time we create a thread. Okay, so let's talk about this entry point. What is an entry point? So entry point, when you create a thread, if you remember from 252, you give it a function. You say, this is the function I want this thread to run. Now, if it is a kernel thread, you remember we have kernel threads and we have user threads. If it is a kernel thread, we can just jump to it. We can just put the address of this guy and then go there. Because this, we are in kernel mode when we're running this thread switch, right? So we're going to go from kernel mode to kernel mode because we're going to run kernel thread. So we don't need to do any mode switch. We can just jump directly to the function that we want to run. This is different if we want to start a user thread. Why? Because this requires a mode transfer. Because now that we're running this thread switch, we're in kernel mode, but then our user code has to be run in user mode. So this requires a level of indirection. So we probably want to first jump to somewhere, some kernel code that would then jump to the function and change the mode to user mode. Because if you can see here in this thread switch, I'm not changing the mode anywhere. I'm just returning, right? So here is where the level of indirection comes. I want to jump to somewhere and change the mode to user mode. So the entry point for the user that you could potentially use, and this is what we are using in RTX in the starter code for the labs, we use the handler exit. So just to remind you, I'm going to go back here. Here was the handler exit, if you remember, right? And I told you that this return changes the mode from kernel to user mode. And this is perfect for us, right? Because we can now jump to our user mode, user code, and change the mode at the same time. Now, this requires us, if we're going to jump here, if we are going to jump to this handler exit for our entry point, then we have to note about this, because now the handler is going to pop some registers and then return. So this is the third thing that we need to push when we're creating our threads, because we're expecting, if we're going to jump to this handler exit, for something to be popped from kernel stack. Therefore, we have to push it when we create the thread. So now 3 elements so far. This is the third element that should be pushed. And then there were 2 more here. So there was here the dummy stack, the dummy, and this entry point. Now, with all that introduction, let's look at the code for creating a thread. We saw everything. So here is the code for, this is the code for creating a thread. Let's actually go through it line by line. So this is the function. So the input is a function that we want to execute and the arguments. And by the way, I'm just focusing on user threads. The code for kernel thread is a slightly different because of the entry point, as I mentioned. So if you go to actually to your starter code, I'll show you in the starter code. So I'll show you this in the starter code. But anyhow, so this is just note that I'm talking for now about creating user threads, because again, the entry point is different for user threads and kernel threads. So I'm going to focus on user thread at this point. Okay, what am I doing? first I create a TCB. Some steps I'm just glossing over, so that it definitely has more stuff to do, right? But I'm just giving you the big picture. So create your TCB, then allocate some space for your for the kernel thread, sorry, kernel stack. So this is the kernel stack. Create kernel stack for your task. One thing to note is I'm creating it with the size, and then I'm adding this stack size. Why am I adding this here? I'm adding because, as I said, a stack goes downwards, because I'm going to start doing this minus minus. Because I'm going to do minus minus, I initially add all of it to the pointer so that it points to the end address, and then I go downwards, right? So that's that. Okay, now I created my stack, my kernel stack. Now I need to set it up. So I have to set it up. Remember, there were 3 things that I have to push on my kernel stack if it is a newly created thread. The first thing is where I want to go, the return address, the entry, where I want to start my execution. Well, these are the arguments. I want to start running the function, so I'm going to push the arguments for that function, and I'm going to push the address of the function that I want to return to, right? So this is going to be popped when we do return in the handler exit. This is going to be going there, right? Now, if you remember, before this is executed, the handler exit wants to pop some registers. So here comes when I push those registers. So this is going to happen when you execute the pop in handler exit. So that's why I'm pushing them. So I push those. But before I go to the handler, right? Oh, I actually missed something here. Here, I need to push the handler as well. So after I do this, I have to do here. Sorry, I will update the slides. I have to do this now. Minus TCB SP, and then I'm going to push a handler exit. So I'm pushing this for the context switch to go to, right? And here is I'm pushing the dummy switch frame that will be popped in the thread switch. So just let me think, which one should I push first? The handler exit or the dummy? In the reverse order, I have to push, because this is yeah, I think what I have is now correct, because this is the first thing that will be popped in thread switch, right? The thread switch, the first thing it does, it pops a bunch of registers, and then it returns. Where does it return? It returns to handler. So we're going to go in the reverse order. The first thing, again, in thread switch, we're going to pop a bunch of stuff, and then we're going to return to this handler exit, and then handler exit is going to pop a bunch of stuff, and then handler exit is going to return. Where do we want the handler to return? It's going to return to function, but then within this return, the mode is going to switch from kernel to user. And finally, we just set the state to ready, and we push this TCB to our ready list. Okay. Now let's look at this in our code in the labs. Let me share my screen. Okay. Share this guy, and we go to GitHub. You guys don't have access to my GitHub, but the code that you have is similar. So prototype, RTX, a source. Now let me first show you let me first show you kernel, the interrupt handler. So we're gonna, this is the exit that we're gonna go. We're gonna go to this SVX exit. And as you can see, we're gonna pop a bunch of registers, and then we're gonna return to wherever the stack is holding. So just associate this with the slides that we just saw. Oh, let me make it bigger. Okay, so this is basically the handler exit in the slides. Now let's look at creating a task. This is creating a task. You will have to implement some parts of this guy. In particular, this kallocate stack, you will have to implement it. No, not this one, for the user. So this is for the kernel. You will do it for the user. But anyhow, let's walk through it. So here I'm doing bunch of stuff, giving this this TCB a TID, setting the state to ready. Here is basically allocating kernel stack. And potentially inside, as you can see, I'm going to do this plus the size of the stack, right? This is what you saw in the slides. So kernel is going to be created. Let me put this in case you guys have questions. Okay, going back. Now, what do I do? So this is, I'm going to align my stack pointer. That's fine. Now, here's the part that I told you that it depends if you're creating a kernel stack or if you're creating a kernel task or a user task. And as I said, the entry point is what makes the difference, right? For if it is a user stack, if it is a user task, if the privilege is 0, if you remember in the slides, we added the arguments and the function. So in our labs, there is no argument. So all the threads have to have 0 arguments. So I'm not going to push argument, but I will push the entry point of the function that I want to run in this stack. Then the step 2 was to push the registers for the exit, for the handler exit. So let me go back to the handler. If you look at the handler, you will see that it wants to pop a bunch of stuff. Oh, why did I come here? So here is your handler. This is SVC exit. So here, as you can see, I'm popping R0 to R12 plus SP, right? So I want to pop these. So I'm going to push them here. I push I first create the user stack pointer, and then I pop it, right? I push it into the stack, sorry. And then I push bunch of dummies, just zeros, for them to be popped in the SVC handler when we are returning. So that's a step 2 in the slides. A step 3 in the slides is to push whatever the thread exit wants to pop, right? And this is the part that I missed in my slides, and I had to add just right. This is where we push if it is a user task. I push this SVC restore, which is where I want to go. Sorry, it's here. Apologize. Not exit. We're gonna go here, which is fine. They're the same, sort of. So I push that one. If it is a kernel thread, I just push where I want to go, right? I don't need to push anything extra. And then finally, I push everything that is going to be popped by thread switch. So, and at this point I'm done. So I set up the kernel stack of the newly created thread. Hopefully that was this part I didn't do last term, to walk students through the code so that they can associate the slides with the code. But I think this time I did it, and hopefully now you have a good understanding of what the code does. If you go back and look at the slides and then come back and look at these codes, now hopefully you understand what we're doing. I think previous terms students were looking at this and they were like, what is this that is done here in terms of stacks? Maybe you guys are also thinking that way. Hopefully not, but anyhow, okay. So let's go back to the slides. I have 3 more minutes. I guess I can do a few more slides before ending this lecture. Okay. So where were we? Okay, we talked about this. Now let's look at this in action. Let's remember that code that I had, while 0. So while true, I'm going to compute pi, the next letter, the next number in pi, and then I'm going to call thread yield. And this is going to continue. So let's look at that. So your stack will look at will have the compute pi on top. Sorry, this was I apologize. Oh God, this was not compute pi. So compute pi is the name of the function. Compute. I think here I had next digit or something. And then I would call thread yield. So on top of my stack is the compute pi frame, and then I call thread yield. So I push this guy. Now at this point, somewhere inside, I'm going to call yield. Right? The system call yield is going to be called by the system library. So I'm going to come to kernel, push the yield. Then this yield is potentially going to call run new thread. Let's look at run new thread. So this is a function that then will call thread switch. So this is a function. Let's look at it. So this at the beginning of it, it disables interrupts because it wants to do some scheduling, and you don't want to get interrupted during a scheduling. Now you pick the next thread to run. If this thread is different from what you were running before, then you make it ready. So this becomes your new thread. You then add your current TCB to the list of ready ones, right? Because you're context switching it from it. So you found a new TCB, you made that new TCB ready, you make this TCB waiting, you make the new TCB running, and this old TCB, you make it ready, and then you call thread switch. Now what happens? You go inside thread switch. If you remember the code for thread switch, what happens? You go inside with this running TCBs stack, and then you get out of it with the thread that you want to context switch to. So we're not going to come back from that back here, right? So at this point, this thread that was running is going to be the state has changed to waiting, and we're not going to come back to it now. Now later on, the thread that we context switched to is going to call yield, or an interrupt is going to happen, or something else. And when that thread calls thread switch, then we come back to this guy, right? At some point, we're going to come back to it, and then we're continuing. So then when we come back, this line is going to be executed when we context switch back to this thread, right? This is an important point. So we're not going to immediately come back to this line. We're going to come back to this line later on when we context switch back to this thread. And when that happens, we just change the state back to running, because now we're running again. We might do some housekeeping. We enable interrupts and go back. So somebody is asking, where are you re-enabling the interrupts? That's a good question. So I said I disable interrupts and then go here, and I'm not going to come back. So who's going to enable interrupts? So whoever is on the other side, we're going to go to that guy's new thread. So we're going to go to somebody else's run new thread. And when they get out, they're going to enable interrupt. So this enable interrupt is going to be executed in the context of the chosen TCB. So that guy will enable the interrupts, not us. And then that guy, at some point, disables interrupts, context switches to us, and then we enable interrupts. So this is kind of like we're passing it to each other. So one of us disables interrupts, the other one wakes up and enables interrupts. Then that other one goes to disables interrupts, and then we enable interrupts. So on and so forth. This is a convention between threads that I actually have a slide for that. Okay, as always, I'm over time, so I'm gonna stop here. If you're interested, you can actually look at this code as well. So this code also exists in your project. Just search run new thread in your RTX, and you can see this code as well. Similar, right? Not exactly this code, but similar concepts. So you can actually associate the slides with the code, and that should be hopefully helpful to do the projects. Okay, so thank you so much for those of you who attended. And thank you for those of you who are watching. Please, if you're watching this after the streaming, try to come to the lectures. It's much more fun when I see more attendees and I get more questions. It's really not good to compare, but in whoever says that and then says but, they're gonna do it. So sorry, I'm gonna compare, but in the other class, the SE350, I have less students in the class, but I have more than double attendees, or maybe double attendees. So try to come to the lectures. It's more fun for me, and it's hopefully you get to ask your questions. Thank you. Take care. Be safe. Talk to you on Tuesday. Bye-bye.